This talk presents the recent development to the CHIUW multiphysics simulation software, CHEMS. This presentation was done by myself, Frédéric Plante, postdoctoral researcher, my colleague Michael Gagnon, who graduated with a master's degree, and our research director, Eric Laurando, professor at Polytechnique Montréal. I will start by presenting the context for the development of CHEMS, then presenting the general development of the software, and finish with two new features, the global stability analysis and the Overset method. The context for our project is that the aerospace industry requires more methods to modelize the performance of an aircraft. And this can be done by using a real scale model, but this is far too risky and costly for optimization of a new system. Wind tunnel can also be used, but the construction of a mock-up and the operation of wind tunnel is also very costly, and maintaining the correct scale is a challenge. For this reason, the industry relies heavily on numerical simulations. However, there are some challenges in the application of simulation to design. First, we need a robust method because we need to be able to integrate them into design loops where we have thousands of simulations that are run without failing. We also need to have fast computation since, for example, the aerodynamic system of equation can have billion degrees of freedom. And this will require the use of HPC. Another challenge is the problem of using multiphysics. So we need to be able to take multiple physics into account, like aerodynamics with structure, to be able to improve aerospace systems. And the precision of the simulation are also a challenge. In this context, Professor Eric Laurando has a fundamental calendar research chair and an industrial research chair, in which we develop algorithms for the aerodynamics, aero-icing, and aero-elastics simulation. In the field of aerodynamics, one of the subjects I will be touching in more detail in this presentation is the prediction of the edge of the flight envelope. And in terms, we want to apply these methods to do aircraft design. For this reason, this involves some challenge for an academic laboratory like ours, since we must develop applications which are close to the industrial one. So we have the same challenge of robustness, precision, and that are involved with this. So we need to be able to do high performance computing. But the people working in the lab, so myself and our graduate student and undergrad student, mostly come from a mechanical engineering background. So we need them to be able to learn how to do high performance computing within a project of 2 to 4 years, plus producing new research work. So this is something that is a challenge for our laboratory. In this context, we chose to use CHIUW in 2019 to develop our new 3D computational fluid dynamics solver. We selected it since it is a viable alternative to the classic C and C++ with MPI paradigm that we were using before CHIUW, and that is used for most of the solver in our field. One of the key features that is very useful is the global namespace, since it allows us to do more rapidly the parallelization on distributed memory. And we make use of many features of the language, like the domain, the list, the set, to code our algorithm. So this makes CHIUW closer to a Python for us. So we have the very high-level feature that allows us to develop rapidly our methods. Also, we extensively use the object-oriented features to be able to reuse structure across several models. So basically, CHEMS is built to solve linear system equation of the form A times x equals b. And we reuse the same method to assemble the matrix and to resolve the systems of equation across all our models. So I will show a small example of this later in the presentation. So for all this reason, CHIUW covered the need of our laboratory and allowed us to rapidly develop the software with a relatively small team of researcher and graduate student. Since we started the development of CHEMS, the number of lines and the capability of code steadily increased. So here we have a graph of the evolution of the number of lines in the CHEMS software since 2019. And by 2020, so a year and a half into the development of the software, we were already able to participate or reproduce workshops these are workshops that are used in the field to test the state of the art for aerodynamic and aero-icing simulation. So this makes CHIUW a state-of-the-art CFD software for aircraft application. So following this success, I worked as a postdoc researcher on the development of method to predict the edge of the envelope of a flight envelope of an aircraft. You can see here a representation of these boundaries, this envelope. So we have on the y-axis the acceleration of the aircraft, which can be achieved during a turn, in fact. And we have on the x-axis the speed of the aircraft. What you can see in this named stall boundary is a limit where the aircraft loses its lift, and the buffet boundary is a limit where the aerodynamic can become unstable, generating an unsteady flow and cause vibration to the airframe. So these are boundaries around which we need to apply some margin, and their prediction is vital to evaluate the performance of an aircraft and to be able to optimize an aircraft. However, these boundaries, they involve unsteady effects, and carrying unsteady simulation is still too costly for engineering applications. So in this context, we propose to use a global stability analysis, which only rely on a linearization version of the physical model and has a lower cost than unsteady simulation, but allow to predict the bifurcation toward an unsteady flow. And now we'll look in more detail at how this is implemented. So the stability analysis method, it relies on the governing equation of the problem. So in our case, this is the Reynolds-Averaged Navier-Stokes equation, which are written in integral form in equation 1. Then the method proceeds by linearizing the flow around this steady state solution. So this will be called W0 here. And by applying a small perturbation around it and simplifying the equation, we get to have a linear model for the evolution of the flow field. And then by assuming that the solution takes the form of a normal mode, we're able to reduce the problem to an eigenvalue problem, the equation 3 on this slide. So this problem, we need to solve it to be able to detect if the flow is stable or not. So by solving the eigenvalue problem, we will get the eigenvector W hat, which are the special shape of the mode, and the eigenvalue lambda, which contain a real part, the growth rate, and an imaginary part, the frequency. So if a mode has a positive growth rate, it is unstable. Now, solving these eigenvalue problem is quite challenging because the matrix A in our case, which is the Jacobian of our Reynolds-Navier-Stokes equation, Reynolds-Averaged Navier-Stokes equation, yes, is a very large matrix, which can have, it can be of a size of a few 100 million to a billion. So solving this problem is very costly. So to do this, we use an Arnoldi iteration with a shift and reverse transformation. So this is a method that allows us to target specific region of the complex plane where our eigenvalues are located. And because it is an iterative method, it reduces the memory requirement to solve the eigenvalues. So this algorithm, the Arnoldi method, it is written on this slide. So because we're using a shift and invert, we need to find the invert of a modified matrix at the line 3 of this slide. And this is where the main cost of our simulation is located, and the main challenge of solving the eigenvalues. So to solve for the invert of the matrix, we could use a direct solver, but this is far too costly, especially in memory for 3D applications. So we are using an iterative method, the GMRES method, which was previously implemented in CHIUW to solve linear systems of equation. So this algorithm is new, but we can rely on things that already existed inside the software. So for example, the main part of the eigenvalue solver was added to the SolverHandle class of CHIUW. So this is a class that is used to store the right-hand side, RHS here, the left-hand side, LHS. So these are the matrix and the vector of our linear system of equation. And we previously had a solver attribute inside, which was used to select the linear solver applied to these matrix and vector. So I added to this class an eigensolver. So this is a new attribute which can be defined. In fact, we define either a linear solver, so the solver attribute, or the eigensolver to be applied to the problem. So as you can see here, the same class is used for the eigenvalue resolution. And then by comparing these two types of solvers, so on the upper part, we have the GMRes class, which contain the method to do the linear solver, the GMRes linear solver method. And then we call it to solve AX, the linear system of equation. When we're using an eigenvalue solver instead, in the case of the Arnoldi shift and invert, we also need a linear system method to solve the linear system of equation. So inside our procedure to do to solve the eigenvalue problem, which is called eigensolve, we will have a call to the same GMRes method. So this is to show that we reuse some main structure to do this global stability analysis method, and this allows us to rapidly develop the method and use it for application, and to limit the number of the amount of code that is necessary to have a new model inside the software. Now for the application, the global stability analysis was applied to the case of the seventh IAAA drag prediction workshop, at which we are participating at the end of the month. So the workshop, it focuses on the prediction of the cruise performance of aircraft, but we carried out a prediction of the high-speed buffet as well. So here you can see the pressure on the surface of the wing for 4 incidence angle at a Mach number of 0.85. And by doing the stability analysis around these flow, so for the 4 angle of attack, we're able to find a mode that become unstable for an angle of attack of 3.25. So on the x-axis of this slide, you see the growth rate, and on the y-axis, the frequency. So we notice some unsteady and unstable mode for high angle of attack, and these are mode characteristic of the transonic buffet. And finally, looking at the eigenvectors, we can extract the shape of the mode, and together with the eigenvalues, this could be useful for aircraft designer, inform aircraft designer on what to do to delay the occurrence of the buffet and to optimize an aircraft. And to our knowledge, we're the second group in the world able to do this type of analysis, together with Sebastian Tim a few years ago. So this is the state of the global stability analysis inside of CHIMS. Now I will be presenting a second development to CHIMS, which is the Overset method. And the reason for this development is that the computational cost, the computational grid is vital to the quality of the simulation, but it represents 50% of the total man-hour when carrying CFD in the industry. So any technique that help us to simplify the machine process and to increase the grid quality are useful. And the Overset method, it achieves that by separating the computational domain into subdomain, which are meshed with no constraint between their overlap. This is shown on the right-hand side of the slide, where we have the computational domain separated in 4 regions, in which we will be able to do a grid separately. However, using such grid requires a pretreatment to eliminate invalid cells and create a connectivity between the subdomains to be able to achieve that is achieved through interpolation. So this requires finding the cells which are inside a solid, which we'll call hole cut, and create a connectivity. The hole cutting process is done through an X-ray method. So numerically, this means casting rays and finding the points where they pierce the solid surface. And this gives us a discretization of the region inside the solid, which is then used to locate if a grid cell is inside or outside the solid. So this is shown on this slide, and it's an algorithm that will allow us to eliminate cells inside, for instance, a wing in this case. Then the next step is finding the connectivity between the subdomains. To do so, the cells of two subdomains must be compared to find an overlap. This is equivalent to finding if the center of a cell is inside another cell. And this is done by looking at the sign of the dot product between the facet normal, the NE vector here, and the vector between the other cell center, the red dot, and the facet center here. So we have an example where this test will give us a point inside and outside of the cell. And then this is the center of a cell on another subdomain, and we'll use interpolation to transfer the variables from the donor cell to the receiver cell. Now, these processes, they can grow in cost as n squared because we need to compare every cell in every subdomain to every cell in the other. So to optimize that, we use an Oct-tree structure where we have some level of depth that are involved inside the Oct-tree. And we have carried out tests with this method to see the improvement to the performance of the preprocessor when we increase the number of levels in the Oct-tree. But what we find is that initially the cost diminish, so we are able to greatly increase the performance of the Overset method. But then if we increase too much in the depth of the Oct-tree, this has a diminishing return as creating the structure become more costly than doing the actual preprocessing. We have done an application to the Overset to mesh to a case like this one. So this is an aircraft geometry where we use an Overset grid to refine the region at the interface between the fuselage and the wing. So you can see the blue, white, and red grid in here. So we're able to locally mesh the junction between the fuselage and the wing. And doing the application with this grid, what we find is that first, the pressure coefficient on the surface of the wing is continuous. So this is an indication that the communication is correctly done between the subdomains. And the comparison between the pressure distribution of an Overset grid and the single grid, which is a classic approach, shows very little difference. So here, this is a verification that everything is working fine with the Overset. But then what we see is that by using a refinement of the grid around the junction between the wing and the fuselage, we're able to modelize some small flow feature like this recirculation here, which was not present on our single grid, but is very consistent with results of Fun3D here, which is a code from the NASA. So we're able to improve our simulation by using these grid refinement, which are easier to do using the Overset method. So in conclusion, the capability of CHIUW continues to increase. We added a matrix-free global stability analysis method and the Overset capability, which are both applied to a half-wing body configuration to predict the buffet, and do numerical simulation. And what is next with CHIUW that will be participating to the 7th direct prediction workshop in the end of June. And we have 6 papers presented at the IAAA Aviation Conference in Chicago, all done with CHIUW. All the new students in the lab are working on or with CHIUW. So this is all our undergrad and graduate students, and will be participating in the upcoming 2nd ice prediction workshop. So here are our reference, and I would like to acknowledge that this work was supported by NSERC and CRIAC, and the competitions were performed on Compute Canada and Calcul Québec on Beluga and Narwhal cluster. This is the end of the talk, and I will now be available for questions.